Welcome back to the deep dive. If you are staring down a big computer science midterm, you have come to exactly the right place.
Yeah,
We know how dense these topics can get.
right.
Architecture, logic, software, networks. It's a huge stack of information.
It really is.
So our mission today is a rapid, high-yield deep dive into that source material. We're going to pull out just the essentials to make sure you are ready.
And we're going beyond just, listing definitions. We want to give you the actual structure, the context, so you can master these concepts fast.
An aha moment machine.
Exactly. Think of it like getting the master blueprint. We're connecting the physical machine to the abstract math, to the instructions, and then to how it all talks to the world.
Okay, let's unpack this, starting right at the foundation. The
Yeah.
physical machine itself. When we say computer architecture, what are we really talking about?
It's the conceptual design, and that's a vital distinction. It's the rule book.
The rulebook.
Yeah, it defines the operational framework. It dictates how all the hardware, the CPU, memory, your keyboard, how they all work together. It's the difference between having a pile of bricks and, the actual blueprints for a house.
Got it. And once that blueprint is set, the machine has this continuous loop of action, right? What's that rhythm?
That's the IPOS cycle. Input, processing, output, and storage. It's the absolute heart of what a computer does.
So input.
You provide data. Processing.
The CPU acts on it.
Exactly. Then you get the results. That's output. And finally, storage, where you save it for later. It's a never-ending loop for everything a computer does.
And the engine driving the P in IPOS, the processing, is the CPU, the brain.
The brain of the whole operation, handling all the arithmetic and logic. But it's not just one thing. It's actually split into two critical parts.
And this is a classic midterm question, I bet.
Oh, absolutely. You have the control unit, the CU, and the arithmetic logic unit, the ALU.
Okay, what's the difference?
The control unit, or CU, is the conductor. It directs the flow of data, it fetches instructions from memory, it decodes them, and makes sure everything happens in the right order.
So it's the manager, the boss.
Precisely. And the ALU is the hard worker. It does all the math addition, subtraction, and all the logical comparisons. Is this number bigger than that one? Are these two things equal? That's the ALU.
And all of this is happening in what's called the instruction cycle.
Right. Fetch, decode, execute. Over and over, billions of times a second.
Okay, here's where things get really tricky for a lot of people and where exams love to catch you. Memory versus storage. Let's get this straight. RAM.
RAM, random access memory. The most important word to remember here is volatile.
Volatile meaning.
Meaning, if you pull the plug, the data is gone instantly. It's incredibly fast temporary storage that your computer uses for programs and data that are actively running. It's like your short-term workspace.
And ROM.
ROM is read-only memory, and the key here is it's non-volatile. Power off, the data stays. It holds the really essential permanent instructions.
Like the BIOS.
Exactly, the BIOS. The stuff the computer needs just to wake up and start loading the operating system. It's like the instruction manual that's bolted to the inside of the machine.
Okay, to put all this into perspective, let's just quickly touch on the massive scale differences. At the very top, we have supercomputers.
Right. Supercomputers are all about raw speed. They are the fastest, most powerful machines we have, built for tasks that need trillions of calculations per second.
Like climate modeling.
Climate modeling, quantum mechanics, genetic sequencing, incredibly complex stuff.
And on the other end, for big business, where it's more about reliability.
That's the world of the mainframe computer. They are built for high reliability and rock-solid security. Think of big banks or government agencies processing millions of critical transactions every single day. That's a mainframe's job.
Perfect. So we have the physical machine, but that machine has its own language, right? A language of ones and zeros.
And this is where we shift from physics to pure mathematics. We're talking about Boolean algebra.
The logical framework for all digital circuits.
That's it. It's a system of math where variables can only be true, which is a 1 or false, a 0. If you really want to understand how a computer thinks, you have to get your head around Boolean algebra.
And the building blocks of that thinking are the big three operations.
Right. You have A and D, which is only true if both inputs are true. You have OR, which is true if at least one input is true. And then NOT, which just flips the value.
But the real power comes from the gates we build out of those, right?
Yeah.
Specifically, NAND seems to be a big deal.
A very big deal. NAND, which is just the negation of A and D, holds a really special title. NAND gates are universal gates.
Universal. What does that mean for your exam?
It means you can build any other logic gate or not anything using only NAND gates. This is a huge deal for manufacturing because it simplifies circuit design immensely. A classic test question.
That's a huge takeaway.
Uh-huh.
Okay, and we can't forget XOR, exclusive OR.
Right. XOR is the difference gate. It's only true when the inputs are different. One true, one false. Not both.
So if both are true, it's false.
It's false. And its opposite, XNOR, is the sameness gate. It's true only when the inputs are the same. It's basically an equality test.
Now, to make circuits efficient, you have to simplify these long, complex, logical expressions. What are the must-know laws for that?
You absolutely have to know De Morgan's theorems. They are essential for simplifying expressions with negations.
They tell you how not interacts with ND and OR.
Exactly. They show that not A and B is the same thing as not A or not B, and vice versa. It lets engineers use fewer physical gates on a chip, which is critical.
Now the second one.
The domination law. It sounds intimidating, but it's super simple. Anything A and D with a 0 is always 0, period. And anything OR with a 1 is always 1.
It lets you just cut through the noise.
Instantly simplifies parts of an equation. Very powerful.
Okay, we've got the machine and the math it speaks. Now for the actual instructions. Software. Let's just restate that core hardware-software distinction.
Simple. Hardware is physical, tangible. It wears out. Software is intangible. It's just instructions and programs. It doesn't wear out, but it definitely needs to be updated.
And software isn't just one big category. We usually break it into 3 types. Let's start with system software.
System software is the foundation. It manages the hardware and provides the platform for everything else. Your operating system Windows, macOS, is the perfect example.
So it talks to the hardware using things like device drivers.
Exactly. Then you have application software on top of that.
That's the stuff we actually use day to day. Word processors, browsers.
Right. And then there's that third special category, firmware.
Ah, firmware.
Yeah.
The mysterious one.
It's just specialized software that's embedded directly into a piece of hardware, usually stored on a ROM chip. It provides very low-level control. The BIOS on your motherboard is firmware. The code inside your router is firmware.
Okay, so to make sure the operating system can talk to all these different pieces of hardware from different companies, there's a special layer called the HAL.
The hardware abstraction layer. Yes. This is so important.
Why?
Because it creates device independence. The HAL is like a translator between the OS and the specific hardware. It masks the differences. So a program doesn't need to be rewritten for every single graphics card or CPU. It just talks to the HAL.
It makes everything compatible.
It's the reason everything works together so smoothly.
Now, building all this software isn't just chaos. There's a structured process.
Yeah.
If you're asked about it, you need to know the SDLC, the software development lifecycle.
You do. And it starts with stage 1, requirement analysis.
Which is just figuring out what the user actually needs the software to do.
Precisely. You gather all the needs, then you move to stage 2, design.
The blueprint phase.
You're planning the user interface, the database, the whole architecture. After that, stage 3 is implementation.
The actual coding.
The programmers get to work.
Yeah.
Then comes stage 4, which is absolutely critical, testing.
Rigorous testing,
Yeah.
making sure every little piece works and that all the pieces work together.
Yes. And finally, stage 5 is deployment and maintenance. You launch the software and then you support it with updates and bug fixes for its entire life.
Okay, so that's how we build the instructions. Now, let's zoom out. How do we connect all these individual machines together?
Right. Networking. We define them mainly by scope. The most basic distinction you need to know is LAN versus WAN.
LAN, local area network.
Exactly. Small area, your home, an office. The key is it's usually very high speed.
And WAN is wide area network.
Spanning cities, countries, even continents. The internet itself is just one giant WAN.
The physical layout of these networks is called the topology. Let's compare 2 big ones on their failure points. Star topology.
In a star, every single device connects to a central hub or switch.
The pro being, if my computer cable fails, no one else cares.
Right, it's isolated. But the con is huge. If that central hub fails,
The whole network is dead.
the whole thing goes down. Now contrast that with a bus topology.
Where everything is connected to one single long cable, the bus.
It's cheaper, less cable, but if that main cable breaks anywhere,
Again, the whole network is dead. And performance gets worse with more people.
way worse. You get a lot of data collisions. It just doesn't scale well.
Now, managing data flow on these networks requires protocols. And there's a huge choice you have to make: reliability or speed. Let's start with the reliable one, TCP.
TCP, Transmission Control Protocol. It is connection-oriented. That means it establishes a handshake before sending any data.
And it guarantees delivery.
Guarantees it.
Yeah.
It checks for errors. It makes sure packets arrive in order. You use TCP for things where every single bit matters. Web browsing, file transfers.
And the alternative for when speed is everything.
That's UDP. User Datagram Protocol. It's connectionless. It's way faster because it skips the handshake, it skips the error checking. It's often called fire and forget.
So good for things like
Yeah.
video streaming.
Perfect for video streaming or online gaming. If you lose a single video frame, who cares? It's better than having the whole stream lag and buffer.
Makes sense. All this traffic moving around needs routing. This brings us to the OSI model. Let's zero in on two key layers for device communication. Layer 2.
Layer 2 is the data link layer. Its job is communication between devices that are directly connected on the same local network. It organizes bits into things called frames, and it uses physical MAC addresses.
So network switches operate here.
Exactly. Switches live at layer 2. They keep local traffic local. But to get data across multiple networks, you need to go up to layer 3.
The network layer.
And its entire job is routing. It uses logical addresses, IP addresses, to find the best path for data to travel across the entire internet. This is where routers do their work.
Layer 2 is for neighbors. Layer 3 is for cross-country road trips.
That's a great way to put it.
Finally, we have to secure all this. Just give us the quick list of key defense mechanisms.
Okay, 3 you need to know. Firewalls, which are barriers between trusted and untrusted networks. Encryption, which scrambles the data so no one can read it in transit. And intrusion detection systems, or IDS, which watch for suspicious activity.
That was an incredible survey. We've built the whole knowledge stack from the physical silicon all the way up to global networking rules. You should have the landscape defined for your midterm now.
And remember, the key for your exam is not just memorizing the definitions. It's understanding the why. Why is NAND universal? Because it simplifies making chips. Why use TCP for your bank's website? Because you absolutely cannot lose a single piece of that data. Focus on the implication.
And here's a final thought for you to chew on while you study. We've seen the generations of computers defined by their hardware, right? Vacuum tubes, then transistors, then microprocessors, all physical breakthroughs. Yet the fundamental logic, Boolean algebra, hasn't changed. As we push into the next generation with AI and quantum computing, the hardware is changing again, profoundly. But here's the real challenge. What new fundamental logical breakthroughs, not just faster hardware, will we need to truly unlock the potential of those systems?
That's the big question. That's why these fundamentals are so crucial. Use this context, apply this logic, and walk into that exam with confidence.
Go crush that midterm. We know you're ready.